Hello everyone, this is my workshop 3 for CSC 381, and the game I was working on is called Spiral Knights, and I'm Noah Helzerman. Moving on, uh, the goal I had for my Turing machine was that it would try to simulate finishing a level, and to do this, it'll simulate the player moving in a somewhat random way, but trying to target towards the elevator. And the enemy is made to try and move just to be next to the player as if they were getting ready to attack. Just wanted to cut in here and show a little bit of Spiral Knights gameplay so you know what I'm trying to implement and work around. So in this little clip I recorded, you can see that a player can't walk through enemies. So in my system, doing that would be an illegal move that I have to reject. And then if we go over to another clip, in this case, you can go on the elevator even if enemies are on it, and that takes precedence over the rule where you can't occupy the same space as enemies in my Turing machine. So you'll see that in the order of steps that I go and what I handle first. And you can also see it a little bit in the language, how the order goes when I compare. And moving back to the slides now. And the goal is to just have the player reach the elevator, but there are some flaws with my design. There's currently only one enemy, and there's no way to actually defeat it, and there's no way for the player to take damage. As a result, my non-deterministic decider will only reject on languages it doesn't recognize. So for the problem I created, it pretty much will always accept, and I always, it can find a way with the small scale problem that I have. And as I mentioned before, my Turing machine is a decider, but it's also non-deterministic. And here's the alphabet for both the input and the tape. I use $sign to separate different pieces of it. And I also have the hash symbol for the movement area. And these don't really find much use. It was more for like a larger scale. Like I focused on movement for this, but if I wanted to start adding stats, I would separate sections with $signs, and I'd have a new symbol for that. But for now, what's really important are these next four. P stands for player, V stands for the elevator, it's like an arrow down, E stands for enemy, and C is used for the area that I make a comparison. And the Turing machine also works with the numbers 0 through 3. So the language that it can decide and recognize can be set up like this. It starts with a symbol and then a hashtag. And then it will look for P and then 2 values N, a V, and then 2 more values, E, and then 2 more values. But then it'll look for a C that has 4. And these N's can be replaced with any number from 0 to 3. So I have like 2 pairs of values for the player, elevator, and enemy, and that stands for the X and Y values of a position. And then I use the 4 values after C to compare X and Y values for 2 things. So here's the case of the sample input. And from here, you could understand it as the player is at position 0, 0, the elevator is at 3, 3, and the enemy is at 3, 0. I sort of arbitrarily put just zeros after C. It'll replace whatever you have there, so it doesn't really matter, but if it isn't a number, it will have an issue. So from here, I'll move on to a JFlap implementation in just a second. All right, so here I have my JFlap implementation. It's a little laggy on my laptop, so you have to forgive me for that. You can divide it up into specific steps. So if I zoom in here, step 1, which takes place in the top left about here, we're just moving the player character. And 3 things can happen. The first one is it'll take one of these branches here, and what it's looking for is seeing whether or not it needs to move +1 or -1 to get closer to the elevator in that axis. So maybe we start at 0, 0, and then we'll keep in this state until we get to the elevator. And then if it has any value that's greater than 0, then we'll move on to here, where we transition back to the symbol P, and then write over the X value a 1 instead of a 0. If you're already in line with the elevator this axis, you can skip this step. But it'll continue on here doing the same thing for the Y value. But 3 more things can happen, and this is where non-determinism kicks in. This state here is hold axis 1, and what that does is we give the player the chance to just not move in the first axis. And then continuing from that, they could make a move in the other axis, or we can repeat that again and they can stay completely still for this turn. And then the last non-deterministic move that we make is called force shift, and what that does is we move diagonally, and this will be in like both the X and Y axis. And the reason for this is to prevent the player from trying to move into the enemy that's just directly between it and the elevator. So as a decider, I had to make use of some non-determinism to try and get around the enemy that is in the level, otherwise it would potentially loop forever. And then moving on to the next step, here we move the X and Y value that the player has into the comparison area of the tape. So it'll write the X and Y into 2 spots after C in the string. And after that, we'll go here where it happens again, I believe. No, at step 3. Step 3 starts here. That's where we would move the values for the elevator to the comparison section. So this code will look at the first, the X value for the player, head over to C and then write that in. It'll go back, check the second value, and then repeat the same thing. And then it'll do the same thing for the elevator's position. And once we do that, we can make use of this nice little mechanism here, which starts at C. It'll read the 4 numbers in a row. So if the first 2 numbers match, then it'll match the first axis. And then if the second one matches, we have found out that the player is on the elevator. So here's the accept state exit. And at any point where it reads a different value, we'll enter the no match state, which lets us move on to the enemy movement, which is the strip of bacon right here. So from here, all it's doing is the enemy will check its position, compare it to the player, and it wants to move plus or minus 1 in both axes until it's adjacent to the player. So this one's a slightly simpler version of what the player does. And this makes sure that the enemy never walks on top of the player, because we're handling the case that if the player and enemy occupy the same spot, and then we reject because the game does not allow you to walk through enemies. So it'll check the first value after E, and then it'll compare it to the first value after P, and then it'll either adjust the value or keep it the same if it's within one spot from it. And then if we move on to this part, it'll update the comparison values where it replaces the elevator position with the enemy position. And then I repeat the same comparison mechanism, except we don't want it to match this time. So the good route is we find that it doesn't match. If it does match, then the Turing machine will get stuck here and reject, because that's the case where the player ended up walking on an enemy. So if we don't have a match, then we repeat the cycle again, and the player gets to make their move. So I'll do a test run of this. It takes a while because we have many steps, but I'll go with a simple one. Let's say the player is in the top left corner. The elevator is just 1 away. Yep, and then the enemy is behind it. And then we have the comparison value. All right, so if we test this out, it'll first read the input up to P, and then from there we'll branch out and make a few decisions. So it'll both try to take the shortest path, where it's like trying to get a straight line to the elevator. It might decide to stand still in one axis, or it'll make the attempt to just move diagonally. And then if we continue on, another branch gets taken where maybe they don't move at all, or maybe they moved in the first axis, but they stopped in the second. So we'll have a few branches open up, but once we get done with that, everything else runs in a deterministic route. We go through and update the C values. So let's see, which one is the closest one? This one. So for the rest of these, I will remove it, and we can focus on just this one. So right now we can see that C now has 1, 0, 1, 0, and it moved the values from P into there, and it'll go back. Now it's on V. It reads the first character, goes over, places that after C. And it's important to note that what C is looking at is like an XX value and then a YY value. But continue on from there, it goes back, gets the other value, and then it'll place that in comparison. Then we head back to the C, and it'll read a 1, and then it will read another 1, and look at the second value, and it's also a match. And at this point, we accept. That's all I can really show you. I could show you like a fast run of the worst case running time, and how many branches it creates. So let's put the player at 0, 0 again. The elevator will be at 3, 3, and the enemy will be at 2, 2, trying to get in your way. So, oh, the input was rejected. I might have typed that in wrong. Let's see. $, hashtag P. 0, 0, V 3, 3. Enemy is 2, 2. C 0, 0, 0, 0, and then a $sign. So I don't know if anyone has tested the fast run a lot, but with what I currently have, it'll pause and ask you if you want to keep going, because right now it has over 500 configurations. And if we continue, it doubles again, and it just keeps doubling. It starts to get slow, but luckily we find an accepting configuration. And this just shows the step-by-step from like how it gets to this. The nice thing about this is the way this could work is either the player only moves in one axis, or it'll guarantee that it moves diagonally, and in that way it can get around the enemy. Otherwise, there are a few other cases where with just the plain deterministic route, it'll keep trying to go in a straight line and never get anywhere, or even just reject outright because the enemy is in the way. But this is what I have from a Turing machine. Feel free to ask questions about it if you like. All right, coming back to the slides. That was all I had. I wish I could do more, but I'm really happy with what I tried to do now. There's something called Turing blocks that we could use to create smaller pieces of a larger Turing machine. And I believe that the work I did for movement could be simplified down with blocks. Likewise, if I wanted to, I could keep going and create a block just for handling stats and other things. But if you have any questions, feel free to ask. And I love to try more things and explain in more detail why I set it up the way I did. So if I do present again in class, I'll be happy to do that. Anyways, thanks for watching.